Thank you. I'm Brian Greene, and in tonight's program, we're going to explore an idea, really a dream, that Albert Einstein perhaps articulated in the most scientific way in the early years or mid-years of the 20th century, which was this goal that through the decades has been refined. And that goal is to have what he called a unified theory, a theory that would describe all forces and all matter from one consistent, coherent perspective. Metaphorically, maybe even a single master equation that would describe everything. And a little bit more concretely, in Einstein's day, he imagined putting together his understanding of gravity, which is the general theory of relativity, which we will briefly discuss with our participants in just a moment, putting together our understanding of gravity with our understanding of the electromagnetic force. And in the decades that followed, that dream grew to not only include gravity and electromagnetism, but also the nuclear forces, the strong nuclear force, the weak nuclear force. And the goal was to put all of that together with quantum physics into a single coherent package. Now, Einstein did not achieve this goal of finding the unified theory. We have not yet achieved it ourselves, but many of us feel that we are en route toward that unified theory. And what we'll do here tonight is discuss how one particular approach called string theory, which emerged really as far back as the late 1960s, as we'll discuss, really began to mature in the 1980s, and developments have continued on ever since. We'll describe what that is and try to give a feel for where we are in this search for the unified theory. And wonderfully, tonight we have a powerful group of theorists whose work is responsible for many of the deep insights that we have into string theory and physics and mathematics more generally. And they will be our guides to this world of string theory and unification. So let's begin bringing in our first guest, Andrew Strominger, who is the Will E. York Professor of Physics at Harvard University, a founding member of the Black Hole Initiative. In 2017, he was awarded the Breakthrough Prize in Physics for transformative advances in quantum field theory, string theory, and quantum gravity. Hi, Andy. Thank you. Our next guest is Edward Witten, who is Charles Simonyi Professor in the School of Natural Sciences at the Institute for Advanced Study. He's made important contributions to both mathematics and physics and is the only physicist to have won mathematics' highest award, the Fields Medal. Thank you. And finally, we have David Gross, who is the Chancellor's Chair Professor of Theoretical Physics and the former Director of the Kavli Institute for Theoretical Physics at the University of California, Santa Barbara. In 2004, Gross shared the Nobel Prize in Physics for the discovery of asymptotic freedom and the theory of the strong interaction. All right, jumping right in, I think many of us are familiar with this quote that's often attributed to Lord Kelvin, although it's unclear whether Lord Kelvin actually ever said it, but the sentiment is certainly an interesting one to take a look at. I'll read it from here so I can see it. The great principles have already been discovered in physics will be henceforth limited to finding truths in the sixth place of decimals. Now, whether or not this was actually said in those words, I think there was a feeling at the end of the 19th century that a lot of things had been figured out, and maybe what was left were details. People were wrong, but what led, Andy, do you think, people to have at least a certain kind of confidence that maybe physics was reaching an end?
You hear that semi-periodically, that physics has reached an end. We've reached the end of what we can understand, and that happens. But then somebody comes up with usually a completely new and unexpected idea about how to go forward, and something that might have seemed like a small little corner. Indeed, I think when Lord Kelvin, maybe I have the dates wrong, but there was already the Michelson Morley experiment, and that was like, we just have to explain that little experiment. And out of that little experiment grew all of relativity. And so we never know if we make a program about how physics should proceed on into the future, we will surely fail, because the real route is somewhere we can't expect.
Yeah, see,
and that keeps happening and happening.
Now, I was going to move on, but I can't help but jump to David Gross, who was shaking his head throughout your entire answer.
No, Andy's answer is fine. I just don't understand Lord Kelvin. I mean, at that time, there was no theory of matter in any form. We didn't know how stars shine. I can't believe he made that statement, since I have enormous respect for.
Maybe he didn't, right?
That's probably correct. But people love that because it puts, these elitist scientists to shame. How wrong they were.
Well, regardless of whether Kelvin said something like that or not, it is true that lots of things that ultimately became part of physics weren't even part of what physicists even imagined being able to explain in those days. Like, why does copper conduct electricity? That was not regarded as part of physics in the 19th century.
Right. So even our goalposts change over time. Advances allow us to push the goalposts further down. Now, Andy mentioned relativity, and of course, one of the big developments after that statement, whether it was actually said or not, but certainly after Lord Kelvin had made his major contributions, was the discovery of special relativity and then the general theory of relativity. And I want to jump right to general relativity, Edward. We had a theory of gravity that Newton gave us. It did a pretty darn good job. There were certain things that it seemed to leave out, like how does gravity actually exert influence from place to place? Einstein comes along and gives us a new paradigm in terms of like warps and curves in space-time. Can you just give us a feel for this new way of thinking about gravity?
A very simple assignment. So first of all, why did Einstein reject Newton's theory? It was not, he had already discovered special relativity, which taught us that, first of all, familiar ideas break down when velocities are close to the speed of light, and that the speed of light is really a fundamental limit that you can't go beyond. In Newton's theory, there was instantaneous action at a distance. That had bothered Newton and many of his contemporaries philosophically, but there didn't seem any contradiction with anything they knew. To Einstein, there wasn't.
And just very quickly, so you mean, obviously, if you change the position of the sun, the Earth will immediately feel that change, right? Yeah.
That was true in Newton's theory. It did bother people, but it didn't contradict anything they knew. To Einstein, it contradicted what he knew when he had discovered special relativity, that the speed of light was a fundamental limit. And more technically, Newton's theory didn't have the right symmetry of special relativity. It has what later was called Galilean symmetry, which actually was roughly formulated by Galileo, although not quite in a modern sense. It did not have Lorentz invariance, which is the name we use for the symmetry of Einstein's theory. So he knew that Newton's theory had to be wrong and he had to do something. But what I've always found surprising, there is actually a simple theory that is consistent with special relativity and with experiments of the day, the Nordstrom theory. And I've always been amazed that Einstein didn't invent that one. It's so much simpler than general relativity.
I'm sure he considered it, but there was something else that Newton had implicitly, but didn't make a big point of, was the equivalence principle, the fact that the source of gravity, what we call gravitational mass, and the inertial mass that governs motion of particles were proportional, identical, which is why all bodies fall with the same acceleration, no matter what they're made out of, which supposedly Galileo had observed and formulated. Newton just took that as a fact. Einstein thought that was incredibly deep, had to be a reason for it, and he used that to motivate his theory. But I think the real motivational force, aside from the conflicts with special relativity, were the fact that Einstein was always governed by the idea that there's no privileged observer, not just inertial observers moving with constant velocity, same physics on a train moving at constant velocity as in this room, where we're all at rest, right? With respect to what? But anyway, he also wanted to generalize the notion to accelerated observers as well, and that led him, together with the equivalence principle, to geometrize.
So let's even just show the geometry just so people get a feel for it. Many of you have seen graphics like this before, but basically Einstein says a body like the sun warps the space-time region around it, and then other objects, say here the planets, move in these interesting trajectories because they're kind of rolling along the warps and curves in the space-time environment. So it's a very beautiful way of incorporating the equivalence principle, a very beautiful way of resolving the issue that Edward raised, because if you were to shake the sun, it would send a ripple in the fabric of space that would need to travel from the sun to the earth. It wouldn't be instantaneous. Indeed, it would travel at the speed of light. And again, just to show that Einstein wasn't just thinking in pictures, we can bring up Einstein's equations as well, just to know that there's deep mathematics that captures all of that geometry. Great, so this is one big development that happened after it was perhaps said that the only new things to be discovered were in the sixth place of decimals. The next thing, of course, that was discovered, although I'm talking atemporally right now, but quantum mechanics was also a big one. So an equally challenging assignment, Andy. Can you just give us a sense of what quantum mechanics is and why were we led to it from our observations of the world?
Is this harder or easier than the assignment you gave?
I think it's actually a little harder.
Okay. So you might think that you could measure perfectly where I'm sitting here, and you might also be able to say I'm completely, perfectly still. But according to quantum mechanics, that's a logical impossibility. If my position is known exactly, I've got to be wobbling around. So there's some uncertainty in how well you can describe both the position and the motion of any object. And what's so unusual about this is maybe it's the first thing that happened in physics that was really, really counterintuitive. The nature of physical objects just isn't what we think it is. We think it's described by their position and their motion, but it's actually, those are only approximate concepts that come out of the Schrodinger wave function. There is something that is completely well described, but it's indirectly related to the things that we intuit are properly described. And I think with quantum mechanics, we entered a realm where our intuition was as not a good as a guide as it had been during the previous centuries.
In fact, we were forced, as you say, to revise our very language that we use to describe reality. Before quantum mechanics, as you're saying, it was where things are and how they're moving. That's the data of reality.
Yeah.
Quantum mechanics comes along and says, whoa, you can't even specify those features at the same time. And indeed, it transitions instead to a probabilistic language in which the best you can do is talk about the likelihood of something being at one place or another. Now, Edward, how would you grade general relativity and quantum mechanics on their own? I mean,
well, they're each stupendously successful in their own terms.
Yeah, I mean, amazingly so. And yet, when we are forced to do calculations that put general relativity and quantum mechanics into union, I mean, what happens?
Well, we get a mess. But before we get to that mess, we perhaps should mention that it's difficult just to combine quantum mechanics with special relativity. But that was done successfully and led to what's really our most powerful theory in the microscopic world, quantum field theory.
Yep.
Also our most difficult theory, I believe. So That part of relativity does work with quantum mechanics and is amazingly powerful, and is powerful in a way that greatly accelerated the progress of physics in the 20th century. But if we try to include gravity, yes, we get a mess.
And by mess, often we say the calculations all yield sort of a nonsensical answer.
They give nonsensical answers. At the beginning, quantum field theory was not well understood, and people did not know whether to take this seriously. But when the other problems, many of the other problems were solved, and this one remained, it came to stand out.
And the way the nonsense or the results that make no sense often crop up is you do a calculation, and sort of regardless of what the input is, you get infinity as the output. And infinity in this context doesn't mean big. It just means we don't know what we're doing. Somehow, when you put the laws of the big, general relativity, laws of the small, quantum mechanics together, it doesn't quite work. Can you give us a feel for why? Or if you want to go to, I think I just interrupted your chain of thought, so feel free to go wherever you want.
No, it's not just it's the lack of predictability.
Yeah.
So in treating quantum gravity by using the framework of quantum field theory, we could do pretty well if we had experimental evidence to try to predict. But we'd have to introduce new parameters.
Yes.
So with our modern understanding of the theory of quantum fields, we have ways of temporarily dealing with infinity. Of course, ultimately, we would like to be completely predictive. And that is, in a sense, the problem. We could, at any energy scale, and so far we have not been able to achieve energies to test the quantum effects of gravity, we could construct a framework, but at the price of introducing new parameters. Unlike the theories that Edward discussed, where quantum field theory has given us a very complete and a finite number of parameters, we can predict thousands of experiments with great precision. In quantum gravity, ultimately, we would appear to have to introduce an infinite number of parameters, which means, in a sense, we can't ever predict
anything. Yeah.
Everything.
Yeah, right.
And scientists such as Einstein, and now more and more of us with the successes of our theory of elementary particles, say, have the dream of predicting everything.
Right.
Or at least a finite number with a finite number of parameters.
Yeah.
And that the quantum field theory approaches to quantum gravity do not seem to yield. They have been tried now for 70 years, which takes us to an approach which might be able to do
Well,
that.
before we get there, though, I want to just spend a moment giving the audience a sense of the achievements that you are referring to in the more conventional approach that Edward mentioned of quantum field theory. Andy, if you don't mind, I'll throw it to you again. Quantum field theory, the operative word is field. You just give us a feel for what a field is and sort of how particles are related to them.
Well, quantum field theory, at first instance, as Edward alluded to a few minutes ago, it's a theory which consistently puts together quantum mechanics with Einstein's dictum that thou shalt not go faster than the speed of light, namely special relativity. And that was really quite an achievement, putting that together. It really occupied a huge fraction of the 20th century. I'd say that the culmination of the conceptual and detailed understanding of that as applied to the physical world was what David was awarded the Nobel Prize for in the the work done in the early 70s. And we just recently lost a great quantum field theorist, Tom Kenoshita, who calculated the anomalous magnetic moment of the electron to 16 decimal places.
By the way, I was 2 offices down from his, and he showed me it was an incredible amount of calculation.
He spent his life. He started on it in pre-World War II Japan.
Yeah.
And he was still working on it, and many other people worked on it. And this is the most accurate agreement between theory and experiment in the history of human thought. It is just a remarkable achievement of the human mind. And all the more mysterious it is that when we go on to Einstein's next gift to us, general relativity, that we're still up in the air.
So a field then it's a kind of substance that fills space. I kind of like to think of it almost like a steam is filling space, and the field's value is dynamical. It can undulate up, it can undulate down. If we use quantum mechanics to describe the field, we find that on microscopic scales, the field is actually composed of little particles. So the particles, in some sense, are the quantum mechanical ingredients that make up this idea of a field. You know, David, your work, of course, was instrumental in establishing the culmination of this program, the so-called standard model of particle physics. And so this is, a monumental achievement, but you try to put gravity in, problems arise. And as David was alluding to just a moment ago, that takes us to this new approach called string theory as an attempt to ameliorate these problems. So let's move on then to that discussion. And before we do, I just want to ask one question that somewhat surprised me. A while ago, there was an article in the New Yorker where Freeman Dyson, who, of course, was your colleague at the Institute for Advanced Study, was saying that we don't need to put general relativity and quantum mechanics together. Just like use general relativity for where it works, quantum mechanics for where it works, and you don't need to put them together. I have my own arguments, I think we all do, for why that is, but can you just give a sense, Edward, why is it important for them to play well together?
Well, gravity is important for stars, but stars are ultimately made out of atoms. So it doesn't make much sense to use quantum mechanics for individual atoms and turn around and use a completely different and inconsistent theory for the whole star.
Yeah. David, do you want to add some?
I think it's actually inconsistent. If you just treat gravity by classical physics, you'll run into contradictions because after all, objects that, as Edward said, that behave quantum mechanically, we use quantum mechanical theories to understand how stars burn, also have gravitational effects. And it simply is logically inconsistent, it appears to me. I'm not sure there's a rigorous mathematical proof, but it's kind of, for a physicist, it's obvious.
Yeah. And Andy, what are some concrete realms, things that we actually study in which you absolutely have to put them both together to make progress?
Well, so of course, one thing would be if you wanted to compute quantum mechanical corrections to the Earth's orbit around the sun, it would be insanely small.
Yeah.
We'll never measure them. Or if you wanted to compute the gravitational corrections to the energy levels of the hydrogen atom, that would also be insanely small. On the other hand, there's one place where they're huge and where we need both quantum mechanics and gravity, and that's in black holes. And now we're seeing black holes all the time up in the sky, and we need to understand their properties, and we need both. It's clear that to fully understand the black hole the way we understand the hydrogen atom in detail, we will need in full force both quantum mechanics and general relativity.
So that's certainly one domain. The other domain that we often use, of course, is, cosmology, Big Bang. If you sort of run the cosmic expansion as we see here back in time, everything comes on top of each other. Huge amount of mass, small space, you need both general relativity and quantum mechanics. So I think it's pretty clear that this is a real issue, that we have to put them together. And so string theory...
But Dyson,
yes, please.
But Dyson was pointing, to an important phenomena, an unfortunate phenomena, which is that it's impossible so far to directly observe or measure the quantum effects of gravity. It seems hard to imagine how to do that in the near future, for sure. And that is, So partly it was, there have been other people, I'm not sure Dyson was based argument on that for a variety of practical reasons, based on what we know, it seems almost impossible to test for the quantum effect.
Yeah, and we'll find that very same issue with string theory as an example, but we should say out front, any theory that tries to put gravity and quantum mechanics together will face the same challenge that you just articulated.
And that's a fact. It's not a shortcoming of our attempts to do so or of theoretical physics. It's a fact of nature.
Yeah.
We're kind of small and large at the same time. And that's it makes life difficult.
So we're small on cosmic scales, we're large on quantum scales, and here we are stuck in the middle. So Edward, can you give the, in 1980s, 81, 82, 83, Michael Greene, John Schwartz are sort of thinking about this new idea called string theory. Were you working on it? You were obviously aware of what they were doing, but where were you?
I was sort of in the neighborhood, but not seriously working on it.
Yeah. And then, so 1984, they have a breakthrough, and they give rise to this very basic idea. I mean, how would you articulate, a la, say, 1984, the basic idea of string theory?
Well, the basic idea of string theory, at least in its simplest terms, is that an elementary particle is not a point particle, as in sort of conventional physics, but a little loop of string. But when I say that, you have to remember on both sides that there's quantum mechanics. So the point particle is fuzzy because of this quantum uncertainty that Andy told us about, likewise for the string. So you have to imagine a string that obeys quantum field theory laws. That will be hard, perhaps, to imagine. But to explain why it leads to unification, the basic reason is that, like a piano string or a violin string, this kind of string can vibrate in many different ways. In the case of the piano string, the beauty of music comes from the interplay of the different harmonics. A tuning fork produces a pure tone, but it sounds harsh to the human ear. In the case of the string, it vibrates in many different ways, and if string theory is correct, the different modes of vibration correspond to the different elementary particles. So unification is achieved because the different particles are different forms of vibration of one basic string.
So, say in the standard model of particle physics that rightly lauded as our deepest understanding of the elementary ingredients, there is a separate field for the electron, a separate field for the electron neutrino, for the quarks, and so up, down, storm, change, and so forth. So in string theory, that proliferation of ingredients is unified from the get-go.
It's unified, and you can't add extra ingredients even if you want to. You're stuck with what you get. And actually, you should be asking David, because David was involved in the early period when the theory was developing.
Yeah.
But the remarkable thing that, so this attempt, string theory is actually older than 84. It had been around for a while.
68,
it was really, but at that point in time, it seemed possible, perhaps, to construct this unified theory of all the forces that we had a pretty good understanding of already, and had enumerated. You showed I think the list of particles and forces. And when these ideas came along, due to the work that actually all three of us were involved in, it suddenly appeared possible to unite them, and nothing was missing. Yeah. And not only nothing was missing in his attempts to unify, but there was nothing that stuck out that couldn't be included, which still appears to me to be an absolute miracle, or better yet, a clue that something is right in these ideas, although, originally we were all extraordinarily excited. This was a framework in which one could produce, as vibrations of one fundamental object, all the stuff we saw. And furthermore, there was nothing else we saw that didn't fit into this framework. So, okay, here, obviously we're on the clue to find the unique theory that Einstein was looking for.
And I can't help but just jumping in.
That way, unfortunately.
So we'll get to that. I just can't help jumping in. I think I've noted to you, David, but I was a student at Oxford as a graduate student in 1985, and you came and gave a talk at the Rutherford lab, and you described some work that you said your very good student was undertaking, Edward Witten. And it was, there's a most amazing thing to be a student at that time as these new ideas were bubbling up. And one of the most exciting ideas is that gravity is intrinsically within this idea of vibrating strings. I mean, it just comes out so naturally. Andy, can you just describe, like, how does gravity fit into the string picture?
Well, the string is everything. And as Edward started to describe, just as when a guitar string vibrates differently, it sounds differently. When a string moves in a different way, it looks differently.
Yeah.
Now, it turned out to be some very complicated mathematics to understand all the different ways that the string could look.
Yeah.
And if you go through that very complicated mathematics, which the three of us did different pieces of during that period, and out pops the electron, the quark, and even the graviton, the force of gravity.
That's the key
and that
point.
was the most interesting thing.
And just say the graviton is, how does it relate to gravity?
The graviton is to gravity what the photon is to electromagnetism. It is the particle that carries the gravitational force. And David can speak to this better, but the consistency of string theory demands that you have gravity. It's not like quantum field theory. You can't add or subtract. It's an all or nothing proposition. And since it was an all or nothing proposition, it better have everything we see.
Yeah.
And it does. And in the earlier days of string theory, when they weren't using it for a unified theory, it was annoying that there was this graviton when they were trying to scatter protons, which doesn't appear. And then people said, hey, maybe this doesn't solve the strong interactions, but solves everything else.
Yeah. So as you're saying, historically, these ideas first were developed to understand some of the things that you made an enormous mark on, trying to understand the strong nuclear force.
So string theory really emerged. Actually, string theory is now, 55 years old. Really started around 1968 in an attempt to understand the strong nuclear force, which binds, we now understand quarks and anti-quarks together with a color chromodynamic field, which is kind of a generalization of electricity and magnetism. And string theory, we now understand that if you take a quark and antiquark, pull it apart, the flux lines, the force lines of chromodynamics get squeezed into a tube. And so the meson, quark-antiquark pair, the kind of particles we produce in these accelerators, behave a lot like fat strings. So particles is one way of describing what's going on, and very good at short distances where we see quarks moving around, but at long distances, a better description, which by the way we haven't yet completely found, is these flux tubes, we say, or fat strings. That led to string theory. String theory came from experiment, but not experiment on gravity or a unified version of, but rather strong nuclear particles. So, again, as we'll perhaps shortly get to, we talk about particles, we talk about strings, but sometimes they're really the same thing.
Yeah, we will definitely get to that.
They're different ways of looking at the same physics, and that understanding has greatly improved. In attempts to then push that farther, consistently, mathematically construct a rigorous theory of these extended objects, it turned out that one of the extended objects, a closed string, not a tube, but a closed string, had all the properties of gravity. Gravitons, the quanta of gravity. That set the theory back, actually, in the beginning, because that's not what they wanted. They wanted a theory of the nuclear force. There's no gravity. But later, and that was really Greene and
Schwartz
and
Veneziano, Susskind.
Well, not in his framework.
Joel
Scherkel, unfortunately, died young, who realized that, okay, maybe not a theory of, we have a better theory of nuclear force, but could be a unified theory of gravity and the other forces.
Yep. And as Andy noted, when you look at the list of properties of the different ways a string can vibrate, within there you see things that at least look like they could be an electron or a quark, or the particles called gluons of the strong nuclear force, or particles like W and Z bosons of the weak nuclear force. So everything seems to be coming together and unified under this picture. There is one quality of string theory that is probably worth emphasizing now here too, which is we live in a world that has apparently 3 dimensions of space and 1 of time. But when one looked at the mathematics of this string approach, that seemed not to jibe with what the mathematics required. So I just wanted, the idea of higher dimensions is something that sounds deeply mysterious, but I was going to just take 30 seconds to explain the basic idea, and then we can go forward, what it even means to have higher dimensions. So if we could just bring up that little graphic that has point particles. There's a 0-dimensional object, no length, no width, no height. Of course, you can see it, so it does have a little bit just for visual purposes. But if we now copy this particle over, and so that we have 2 of these guys, and we join them together, we find a 1-dimensional object, a line. And if we now copy over this line so that we have 2 of these lines, if we connect up all the vertices, we now have a 2-dimensional object, a square. We play the same game to go to higher dimensions. Make a copy of the square, connect up all of the corresponding vertices. Of course, we get a cube, 3 dimensions. But now we can go further. Copy the cube, connect up all the corresponding vertices, and now we have this beautiful example of a higher dimensional shape, a hypercube, tesseract. And so when you look at this guy here, we are projecting down to a 2-dimensional screen that we 3-dimensional beings can see, but the idea is to go from 0 to 1 to 2 to 3 to 4 and onward. It's not all that mysterious. So we have this, beautiful way of thinking about higher dimensions, but Edward, this is mathematics. And when we studied string theory, where were we led in terms of the structure of space-time?
So string theory, at least in its simplest form, requires 10 dimensions, 6 extra ones. To make sense out of it, we usually assume that the 6 extra dimensions are very tiny, so we don't see them in everyday life. In fact, because of quantum uncertainty, the particles and fields are completely spread over the 6 dimensions.
In fact, we can show a little picture of what that would look like. So, this would be a schematic representation of those extra dimensions curled up. And if you were examining the microscopic structure of space, in some sense, vaguely, it would look like this according to string theory.
I think the first to explain that you could have tiny extra dimensions that you wouldn't see in ordinary life were probably Einstein and Bergman in about 1937. Yes. Regardless, though, in the context of string theory, the extra dimensions are put to good use in the following sense. Probably everyone here is familiar with electrons, but if you're not a physicist, you probably don't know that there are 2 cousins of the electron, the muon and the tau. There's an amazing duplication of particles that we don't understand very well. And extra dimensions, with a lot of more room for the strings to vibrate, are part of technically what goes into the fact that string theory can naturally generate all those particles of the standard model.
And so, going even a little further on that idea, those extra dimensions are made really small, in part because we can't see them. They better be pretty small. But the strings are pretty small too, and as you're saying, they can vibrate into those extra dimensions. And that additional room, freedom for vibration, gives rise to a longer list of properties of those vibrations, which can include more exotic particles, like you say, like the muon or the tau or the other generations of particles. Yes, David?
These, the standard model we have of particle physics, which electron, neutrinos, quarks, are different copies of the same structure, leave all of these, many of these properties of these basic constituents unanswered and perhaps even unanswerable within that framework.
Because you could change it in principle according to the math.
They could change it, and they're bizarre.
Yeah.
String theory really, those first attempts at compactification and using the extra dimensions to produce a specific unified theories was truly remarkable because it gave totally new ways of explaining the multiplicity of quarks, the values for their masses, the strange hierarchy of masses, so on and so on. And it realizes, by the way, a centuries-old goal of Plato to reduce physics to geometry. These properties were really not understandable in simple modifications of the standard model, quantum field theory, but in string theory they sort of had geometrical explanations. Extremely beautiful and appealing, unfortunately.
But before we get to unfortunately, let's revel in where we've gotten. So if we can just do like a little summary of where sort of, I don't know, by 1990s or so we are with string theory. So if you can just rattle off some of the things that summarize. So string theory combines general relativity and quantum mechanics. Huge achievement. Number 2, string theory unifies all forces and all matter, at least has the capacity to have potential, yes, exactly. So I'm being careful with my language here and you're staying on me, which is great. And finally, it offers a rationale for fundamental physics. What you were just saying, David, without this approach, you could put any fields into a quantum field theory, any particles and some, within reason, any properties, but in string theory, you don't have that flexibility. So certainly, like as I entered the field, later on, in mid-1980s, this is enormously exciting. And so, I mean, Andy, as of 1990, what was your perspective on where we were? Were you starting to think like Lord Kelvin, like this may be it? Because some were saying things like that at the time.
I'm afraid I was a prematurely cynical. As you can see, I wrote in some of my. So, there is this very hard problem, which is, it is fantastically hard to measure the gravitational corrections. There's motion.
Yeah.
Quantum corrections, there's motion. Gravitational corrections, the hydrogen atom, and now we could also say we will never be able to make an accelerator big enough that could see a string. And I didn't think we were going to go on and show that, do experiments and verify, already by 1990.
Yeah.
I didn't think we were going to go on and sort of verify it in the same way that we verified the strong and the weak interactions. However, I think I am well known as one of the most enthusiastic people about string theory, and I don't think that is the axis that we want to judge it on. And we will get to those other
things. Do you mind if we judge it on that axis first and just get it out of the way?
So let me just say this. I think it is gets an A++ for being completely consistent with the universe as we know it. It's the only theory that we have that could, in principle, describe the universe that we live in with all its idiosyncratic features.
Yeah.
And that is not a mean feat. But as far as being a theory that we could measure and verify in some concrete ways, it's not logically precluded, but I think it's going to be very hard and would require some luck. And people are working hard on doing it, and they should be, and I'm not criticizing them for doing it. I'm glad they're doing it, but I don't
have great hope for it right now.
I don't have great hope for it.
So let's just turn to then a series of questions, one of which indeed will be the one that you were just speaking to, in terms of just to get sort of a feel of the challenges and the achievements of string theory. So question number 1 is, can we test the theory? Can string theory be tested experimentally? Now, you quickly made reference to the fact that seeing a string directly, I mean, that would be a pretty good test, right? You look down and you see it. But just to give people a feel, at least in the conventional formulation, a string is to an atom as a tree is to the entire observable universe. So that's how small strings are on even atomic scales, and you're right, seeing them directly is going to be pretty tough. But people have certainly put forward other ways of testing them, and I'd like to get your feel for this, because string theory, like the more full name that we often use is superstring theory, and we're not going to do a whole discussion of supersymmetry, which is the super in superstring theory, but many people thought that that would be the key to at least finding circumstantial evidence, or at least some thought it. And so if we could just bring up just what the particles of a supersymmetric theory would be like. It's basically for every known particle, there's a partner particle according to this deep symmetry in the theory for the electron, selectron, for the quarks, squarks, and so forth. Who of you would have been betting on this being our first clue, finding those particles? David?
Well, number one, string theory does not require or imply low energy or easily observable supersymmetry.
Yes.
For me, the clues for supersymmetry were more that it answered other questions,
sure.
which had to do with the structure of the Standard Model as such, the Higgs sector,
Yes.
which is unnatural in some ways, dark matter, which has been observed and we don't know what it is, and supersymmetry offered a nice clue as to how that, why the dark matter content of the universe would be what we have what astronomers have measured it to be.
Yeah.
These clues still remain, by the way.
Yes.
And supersymmetry still, by the way, does remain as a viable candidate, just some portion, certainly not 99% of the potential phase space for discovery haven't been found. So, okay, we've learned a lot from the non-discovery of supersymmetry, and we continue to look for it. As we continue to look for the origin of dark matter, as we continue to try to understand the strange Higgs sector, and so on and so on. So, but there have been a lot of interesting ideas about how one might directly, experimentally observe string theory or test string theory. They just haven't so far worked. For example, cosmic strings.
Yes.
You could have strings produce, the universe inflates dramatically in its early history, we believe, and that can pull these very small strings out to be the size of the universe or the galaxy. And then they would actually function as gravitational lens. The low energy density is so high within the string that they would bend light around it. We would see multiple images, but very different than multiple images from a point lens. So people have looked for that, continue to look for it. Doesn't seem to be there. Such cosmic strings don't seem to be there in abundance, but that would be a way. So it is incorrect to say, I think, that string theory is not testable.
Yeah.
If it's not testable, it's not physics. It is testable. It's just difficult.
Hard, yeah.
It's difficult perhaps partly because we're so small or so big, but also because perhaps we haven't thought of the right tests. There are other tests that...
Well, Edward, you put forward some tests like fractionally charged particles of a particular strange. I mean, and where do you think we are, at least in the journey that should one day perhaps?
I'm sympathetic to what Andy said, which is that we need some good fortune. So yes, we could discover fractionally charged particles created in the Big Bang in cosmic rays. It's not out of the question. You'd have to say we'd have to be rather lucky to discover that, given all that we know.
Yes. Right. So, Andy, any further thoughts on how we should interpret our current state of lack of evidence for supersymmetry, lack of evidence for gravitational lensing by linear defects, lack of finding of these exotically fractionally charged particles? It's just en route to one day having some evidence, or too early to even ask a question like that?
We don't have a map, Brian. If you got a map, give it to me.
Yeah.
Sure. We have some really interesting facts about mathematical physics. We have lots of data, experimental data about the real world of different kinds. Of course, accelerator data doesn't seem to be coming in faster and faster, but there's lots of astronomical data that is just pouring in. And we have, we just need to all keep working on whatever we find interesting.
Yeah.
Because we don't know what the path is.
Yeah. Yeah, David.
But by the way, At this point, with our understanding that I think you're going to come to, especially our understanding of dualities between string theory and quantum field theory, they fit together so well that you could say, and I believe this to be true, that they're part of the same framework, which contains string theory, quantum field theory. And quantum field theory is extremely well tested, and we're continually learning about properties of of quantum field theory, which some of them actually bear on string theory, maybe the string theory of mesons, but that's, continuously connected intellectually to fundamental string theory, to gravity. So it's really hard. One can argue that we can use the real world, which is in our theory, so successful, precise theory of the real world, to make a connection to experiment.
No, it's an incredibly important point, and one we'll come to toward the very end, that the most recent work ties together string theory and quantum field theory in a profoundly interesting and important way. So in some sense, we're not talking about something so radically different. It's just a different formulation. But let's just move on to a couple of other questions, because next question is, does string theory describe a unique universe? Because one of the nice things, Edward, that you were mentioning was the way these extra dimensions are curled up has an impact on the way that the strings can vibrate, which has an impact on the kinds of particle properties that those strings will appear to have. When I was a beginning student, I got very excited about the extra dimensions because I like geometry and mathematics, and there's this beautiful complex geometry, Ricci flat surfaces and so forth. And it seemed like there were very few ways that you could curl up the extra dimensions. And that was very exciting because it seemed to suggest very few universes. That changed over time as people found more and more ways in which you could curl up these extra dimensions from, 5 in like the first paper that you wrote. I think you listed maybe like 5 possible examples or 3 or something like that. And that grew to like 100 examples, 1,000 examples, a gazillion, 10 to the 500 examples, it just exploded over time. So what's your view on thinking about string theory and the goal of having a unique universe come out of a theory?
It's certainly true now that the theory appears to be unique.
Yes.
But we don't see that the solution of the equations that would give rise to our universe is unique. And I have to tell you that observational discoveries are not very encouraging for the uniqueness either. Both the acceleration of the cosmic expansion and the failure, the fact that we explored the energies of the electroweak theory of the Higgs particle without seeing what would account for that energy scale. Both of these raise serious questions about whether we actually do live in a world that is unique in the sense that Einstein envisaged.
So, and when you say that, you imagine if you go like sufficiently far out beyond the cosmic horizon, things in principle could have different properties.
Well, it's a question.
Yeah.
The acceleration of the expansion does not suggest to me that we're living in a world with the kind of uniqueness that I imagined for it, let's say, in the period in the 80s that you talked about earlier.
Right. So we may just have to potentially live with this idea that it may have been asking too much.
It would be nice if that's wrong, but we might have to.
Yeah.
The world was not created for our convenience in understanding it.
Yes, absolutely the case. All right, so another question, Andy. We discussed how black holes and the Big Bang are a natural arena where gravity and quantum mechanics need to come together to understand what's going on. And you and Kerman and Vafa have done pivotal work in understanding black holes. It's a complex subject, but you can just give us a bit of a sketch of how string theory has resolved certain black hole paradoxes that were articulated even with Stephen Hawking way back in the 1970s.
Yeah, so Stephen Hawking and also Bekenstein.
Yes, of course.
They gave us a famous formula. It's the thing that Hawking is most famous for. You can write that formula in many different ways, but one way to write it is that it's a formula that tells you how many gigabytes of information you can store inside a black hole. And it turns out to be proportional to the area. And they derived this in a Hawking derived this in a breathtakingly elegant and simple manner.
In fact, we're showing a little bit of a visual right here. If that's sort of a black hole, the bits, if you will, are stored on the event horizon, the surface of the black hole.
Yeah, it was a very simple argument, but it didn't explain what the bits were made of. So it's as if you took your smartphone and you wanted to know what its storage capacity is, and you just put photos in there, and at some point you couldn't put any more in, and then you know how many bits it has. So he inferred how many bits there are in a black hole, and it was such a simple argument. He didn't need to know string theory. All he really needed to assume that somehow or other, quantum mechanics and general relativity are consistently reconciled, and we believe that just because they're here and they're part of our universe.
Yeah.
So if you have a theory which is supposed to fully explain the inner workings of quantum mechanics and general relativity, it should be able to actually tear the smartphone open and count those bits and see that it agrees with what Hawking does. And so when we first started working on string theory, this problem was already on the table, but string theory was pretty complicated, and we didn't have the tools to do the computation. But then we kept understanding it better and better and better and better. And by the mid-90s, it was clear that we understood the theory well enough so that we could tear the black hole smartphone apart and see what kind of bits were sitting in there. And this was really a moment of truth, because if we counted the bits and they had come out to be the wrong number, string theory would then be inconsistent. And on the other hand, if we got the right number, then we would know that string theory understood a lot about the deep way that quantum mechanics and general relativity is put together. And of course, we did get the right number, and we got the right number with lots of parameters in it, in every situation that we could compute. And it also was one of the main times that string theory solved a problem that somebody else posed. You know, if you have a new assumption about physics, you shouldn't just make your own problems and solve them using it. You want to solve a problem that somebody else has been worrying about. In this case, it had been a quarter of a century that they had been trying to understand this, and string theory gave the answer. So that's one of the feelings, that despite the fact that we aren't going to measure it, I feel we're on to something here, and we should keep going to see where it leads.
So that's a very sensitive test, and a kind of detailed mathematical test of the consistency of string theory, both internally but also with things that had emerged from non-string theoretic considerations. As you say, Hawking wasn't working with string theory, it was just having a kind of loose marriage between general relativity and quantum mechanics, loose enough to be able to do those calculations, but not a full theory, but yet the agreement is remarkable. So Edward, when these results came forward, and of course you've been instrumental in pushing our understanding in so many different directions, but was this a moment for you where it really felt like this was one more piece of evidence that things are really working?
It was very dramatic. So I think the calculation was done in 1996. And that was a period where there was a lot of rapid progress. In particular, Joe Polchinski had discovered a new building block in string theory that we hadn't understood, the D-branes. And that made possible the calculation that Andy and Qumran did. And somehow it was clear that, at least in that example, We then understood the fundamental building blocks well enough that we could count the quantum states of a black hole, which it would not have been possible prior to 1995.
Yeah. And David, so where did this all leave you? I mean, obviously you invented one of the key string theories itself, and here was
enormously
really working.
exciting, and but of course it left open many other questions about black holes. And the remarkable thing is that many of those have been answered very recently.
Yeah.
So the black holes pose many fascinating paradoxes, apparent paradoxes between general relativity and quantum mechanics. The loss of information problem. You know, you throw stuff into a black hole, you can't see it. Hawking told us black holes radiate, eventually disappear. Where does the information go? How does it get out? You know, I remember a time when Hawking, actually it's about 50 years ago, Hawking posed this problem, and it led to a really serious debate between sort of the particle theory people and the general relativists, quantum people, class and general, because Hawking really was saying quantum mechanics has to be modified. Quantum mechanics is wrong in a sense. Information is not preserved. And the quantum field theorists by and large said, no way. And this went on for quite a while, and I'm not sure everyone agrees that it has been resolved in our favor. Hawking eventually agreed, but the recent advances in understanding where the information is stored within black holes and how it eventually is recovered outside has been amazing.
Yeah.
And I think the problem is clearly resolved.
Right.
With the triumph of quantum mechanics.
Totally agree.
I would argue.
So, Albert, I want to just turn to one other question, which is not directly in the realm, say, of physics, but has string theory inspired breakthroughs in mathematics? This is an arena where there's been so much. Can you give us a sense of why string theory has had the impact it has?
I'd say string theory has had a lot of impact in mathematics, but so has quantum field theory.
Yes.
Since the development of the Standard Model. Once the Standard Model was in place, which was by the mid-70s, physicists started needing mathematical tools that were unfamiliar. And in turn, it turned out that physicists were sometimes, inspired by quantum field theory and later by string theory, able to make predictions about mathematics that came as surprises to the mathematicians. In some sense, quantum field theory and string theory have deep truths, but they're very difficult subjects mathematically, and the people who work on them tend to be physicists, therefore. And as long as that's the situation, I think physicists will be able to continue to surprise the mathematicians with some of those insights.
Yeah. And you know, one of the other key reasons within the string theory context is we've needed to bring in so much mathematical architecture in order to understand these higher dimensional spaces and the surfaces that strings sweep out as they move. So there's so much opportunity for a crosstalk between the two that, you know, even if string theory were to go away, let's say your calculation of black hole entropy had not agreed with Hawking's, the mathematical contributions of string theory would stand because they are beyond any particular test. Thankfully, though, it all seems to be working out. But I do want to turn now to, in our sort of final subject, what many consider the most important collection of recent advances that will take us right up to the moment. And they all go under the heading of what's known as duality. And, you know, just want to give people a feel for what we mean by duality. So I'm going to start with just a couple of very, very simple examples just to give a feel for it. So, you know, if you consider a concept expressed in two different languages, the dog jumps. Now, I can't pronounce on the right, but you probably can, Andy, since, you know, I think you are relatively fluent in Chinese, but I won't put you on the spot. But here we have one concept, the dog jumps, in two different languages. They're dual to each other. They are expressing one and the same abstract concept, but obviously in very different ways. Another example of duality is Arabic numerals versus Roman numerals, 3 expressed in 2 different ways, or the number 16 in 2 different ways. And I like this example in particular because when it comes to the dog jumps, whether you express it in English or Chinese, you're basically communicating the same information in more or less the same parallel way. But with Arabic numerals and Roman numerals, if you ever try to do a calculation with Roman numerals, it's pretty tough to do that calculation on the right-hand side, but it's pretty easy to do it on the left-hand side. So the point is, when you have dual descriptions of the same idea, sometimes there is a great benefit in using one approach versus the other because one approach can give you more insight into certain things than the other. And this is what we have found in string theory in spades. And so we'll get to the sort of the most influential of recent times. It's called ADS-CFT duality. It's a complex name for something simple. Let's not go to there yet. But Ed, I first want to just start. Yes, is it wrong?
Is there something that Roman numerals are better for?
That's an interesting question. For confusing 6-year-olds, maybe that's one.
Because usually in a duality, one side is good for one thing.
Yeah, but I want the other duality is good for something else. Yes, I agree.
Yeah, that's really what I was going to say as
Yeah.
well. In our dualities, neither one is better than the other. They each are better for their own purposes.
For own purposes, yes, right. So we'll have to come up with a purpose for Roman numerals, but I can't do it. I cannot do it on the spot.
They look good.
They look really good. Yeah, I mean, come on. Yeah, exactly. Thank you, Andy. So Edward, you articulated a whole collection of dualities, which really helped us with not really a problem, but an irritating quality of string theory that as it was developed, there were many different versions of string theory. So David Gross and collaborators developed what technically is called the heterotic string. And we had the type 1 string and the type 2. They're all based on vibrating strings, but they look different in detail. And then you found that those differences were kind of like the difference between Arabic numerals and Roman, roughly speaking. So just tell us what you found.
Well, I found some pieces of that. Many colleagues had found other pieces. As it was developed by the mid-'80s, there were 5 different consistent versions of string theory, which differed by properties like whether the strings are loops or could also be open strings with ends, and whether they were electrical insulators or electrical superconductors. And of course, there was a mystery if one of those 5 theories describes our world, who lives in the other 4 universes. It turned out, though, as we understood by the 90s, that the 5 different string theories are different limiting cases of the same unified theory, which is the candidate for superunification. Under different physical conditions, one or another gives a better description, a more economical description and easier to calculate. But they are all different limiting cases of the same theory.
And so all of a sudden, not only was string theory a unified theory, gravity and quantum mechanics, capable of unifying all other forces, but now the different string theories were unified into sort of a mega unification, which was a very powerful kind of duality. And there were many other dualities that we just don't have time to describe. A number of us were involved in dualities to do with the shapes of the extra dimensions in string theory and so forth. But I want to turn to the ADS-CFT duality that, David, you already made reference to. This is an intimidating name, anti-de Sitter space conformal field theory duality. You don't have to memorize the name. What I'd like to do is just try to give people a feel for this. I have some visuals in a moment that will attempt to do so. But David, can you just give us the broad brush perspective on what it is and what it tells us?
Well, we had to do
We're listening.
So the universe is kind of big. It would be nice to put it in a box, which is difficult to do in quantum gravity or gravity in general because the walls of the box have mass and they pull. But there was a turns out, a kind of Einsteinian space, solution of Einstein's equations with a cosmological constant, the opposite sign of what we observe, curves the universe in the opposite way and creates a box. That's very useful, it turns out. I'm not discussing how this arose, but what it consists of. And a box means that there's a boundary at the box, and you could ask, what is the physics on the boundary? And it turns out that in string theory, in a space where 5 of the dimensions are a kind of box, and the other 5 dimensions are curled up into a sphere, the box has a very simple description, the dynamics on the box, very simple description in terms of ordinary quantum field theory with rigid geometry. So there the space-time is fixed and looks very much like that geometry in this room. And no dynamical gravity, no general relativity if you want, no need to do quantum gravity, just ordinary quantum field theory. And starting with these strings in 10 dimensions, the physics on the boundary is that of a close, very beautiful, elegant relative of the standard model.
Yeah.
The same kind of physics. So this is not totally coincidental, based on what we previously understood at all, but the precise mathematical equivalence of these 2 descriptions is of enormous value to us, which is why it's dominated speculative research in this field for the last 25 years, completely, because it allows us to explore string theory using well-established, experimentally verified, if you want, tools of quantum field theory to learn about black holes, quantum gravity, string theory, and vice versa. In the regimes of string theory, which after all is a generalization of Einstein's equations, in cases where we can solve Einstein's equations and use them, we can learn about problems or issues in quantum field theory, which are extremely difficult. So it goes both ways.
Yeah.
But most importantly, it ties a theory of just a quantum mechanical theory with rigid geometry before Einstein to quantum gravity, to dynamical space-time, and it produces higher dimensions, at least one higher dimension.
Yeah.
So it is the basis of a feeling that has existed in string theory for a long time, that space-time itself might best be viewed as an emergent concept, in this case from a hardly ordinary, very difficult quantum field theory. And suggests that we have 2 dual descriptions, which, as Edward said, one is good sometimes, one is good in other regimes. They surely emerge from some unified description, which we don't know. But if they do, it is extremely unlikely that space-time, the way we understand it, will be inherent in that more fundamental representation. I think much of what we're making advances in trying to explore is what is space-time made out of? How do we understand the emergence of space and especially of time?
So that's actually a final question I'd like to get to in just a few minutes. That was a beautiful summary of ADS-CFT duality. We have some visuals just to underscore exactly what you just said, and just to sort of give the audience a sense. This is the box, in some sense, that you're talking about. All we're going to do with 3-dimension, latitude, longitude, and radial direction. And if you were to take away the top of the box so you can sort of see inside this spherical box, as you're saying, the outside in this lower dimensional version has 2 dimensions. The inside, which often in the field is called the bulk, this blue area, has 3 dimensions. So there you have a difference of dimensionality between the outside and the entirety. And then if we keep on going, the idea of the duality is that if we have strings vibrating in the inside, That's equivalent to point particles that you can see living on the outside. So a particular kind of quantum field theory on the outside where there's no gravity being completely equivalent to a quantum gravity theory because it has strings that are vibrating within the inside. So if we can summarize what we're finding with this, exactly what you just said, David, you have a rigid geometry on the outside, you got a flexible geometry on the inside, and yet these two theories are meant to be as dual as, 3 and, 111 in Roman numerals, right? And so if we can go just to the summary slide of all what we find here, we have on the far left, we have this idea that a theory that lives in a lower dimension, the yellow, is equivalent to a theory that lives in higher dimensions. This blue area showing that dimensionality is somehow some emergent property, not fundamental. If we go on to the next one, a theory of point particles, field theory on the outside, equivalent to strings on the inside, that's your point. That field theory and string theory are part of the same overarching rubric. And finally, just to reiterate that last point, a theory that has quantum gravity on the inside being equivalent to a theory with no gravity, rigidity on the outside. And of course, we should mention Juan Maldacena was one of the key people where this idea culminated. And of course, everybody on this stage has made important contributions to this duality and the implications that it has. So I just want to spend the rest of our time, Andy, what do you make of this particular duality? How does it change your thinking, say, on the nature of space-time, the very arena of reality?
First of all, it's incredible the amount of, you've made some pictures here which don't capture the incredible amount of structure that is involved, the self-consistency of having a theory on the boundary that was equivalent to the theory in the interior. And I guess I'll say some words which you haven't said so far, the so-called holographic principle.
Yes, please, yes.
So the holographic principle is precisely that theories of quantum gravity, which we really still don't understand in general, and we don't know how far we are from fully understanding all of the quantum theories of gravity, including the ones that might describe the real world, including many things about string theory. There's still a lot we don't understand. But I think of the idea as originating in the work of Bekenstein and Hawking. In that picture you drew a similar picture where you had bits
on the outside.
You had bits on the outside, and that had nothing to do with string theory.
Yes.
And so, and indeed, the thing that Vafa and I did was one of the first examples of there were other ones. For an early example of some sort of holographic duality of this type. And it works so well and reconciles so many puzzles, one hopes that, or it's interesting to investigate the possibility that it is completely general. So the context in which we understand it very well are the ones that come out of symmetry, in which out of string theory, in which you have a universe with negative curvature. And I think there is the hope there, and this is an important program in our field now, that there should be some way to generalize this beautiful relationship to universes like the ones we inhabit, which are nearly flat, or even in a better approximation, are expanding to the infinite future. So that is a very exciting problem to think about. We clearly don't understand everything about it yet, but we understand an amazing amount in some specific cases.
Yeah. So Edward, I'm interested in your thoughts on how your views of space-time have evolved as discoveries in physics and string theory over the past few decades. And in particular, one of the really interesting results of this kind of physics has been to relate, quantum entanglement, the connections between different parts of the outside, the boundary, the yellow region, that in some sense is encoding the way space-time in the interior is sort of knitted together. Where does this leave you thinking that what the nature of space-time is?
Well, to be more conservative, I would just say that we've suspected that the difficulties with understanding quantum gravity have suggested for a long time that the space-time continuum, as Einstein envisaged it, might not really exist at very short distances. And ADS-CFT has given us an inspiring example that we actually understand where space-time emerges from something else. Unfortunately, we haven't been able to generalize the lesson in whatever way it should be generalized to apply to the real world, as Andy was telling us a moment ago. So different discoveries over the time, but maybe ADS-CFT was the most dramatic, have given us a much more concrete understanding that in some sense space-time should be emergent, but we do not have a systematic picture.
And can you give us a feel, David or Edward or Andy, when we say space-time is emergent, what would that mean? Like starting with a theory that doesn't have space and time to begin with, and then space and time somehow arise from the dynamics of the theory? I mean, David?
Oh, we don't know, but obviously. But we have this example.
Yeah.
In some versions, you can say that all of space emerges. We have formulations of string theory and 10 dimensions which are based on a pure quantum mechanical theory with no space. So they're just degrees of oscillators. That's quite remarkable. So given that example, it is very reasonable to expect or a combination that this is general, that all theories which are based on some kind of space have formulations which are at least dynamical space.
Yeah.
Time, however, is somewhat different. Time is always the most mysterious of all of our concepts. And none of these examples truly have emergent time. And it is extremely difficult for a physicist to imagine formulation of physics which doesn't have time in it from the beginning, because the whole point of physics is to make predictions. Given what we know now, to predict it. But if there's no... And among the many open questions that Edward said we need to do, generalize this emergent space to other situations, we definitely need to understand what time, which Einstein brought together with space in both special and general relativity, in what sense could that conceivably be an emergent concept?
Emergent has time in it, sort of.
The place where this hits up on one of the other fundamental problems that faces physics for the first time is the beginning of the universe.
Yeah.
We are forced by our understanding of cosmology, extrapolating back, to consider the earliest possible moments in the universe. What does that mean? And what does it mean to have a theory of the initial conditions of the universe? How did it begin? Is it unique? These are questions physics has never been forced. We ignored it. Never been forced to address, but now we are. We have no examples of successful theories of the origin in science, not religion. But so I think these are all connected and are at the core of the most difficult conceptual problems that we have been forced to consider. And 40 years ago, we were happy to ignore those. All we wanted was a theory that explained the properties of the standard model we couldn't calculate.
Right. So we only have a few minutes left, and I just wanted to come to some final articulation, however you define that, for where we are in the state of string theory. And look, all of us are professors. We all have that awful task of grading students. Although, Edward, maybe you never need to grade students.
Well,
You've avoided that
once upon a
completely.
time.
But however you want to define it, imagine a student called String comes to your office, and String has done some pretty cool things. Put together gravity and quantum mechanics. Been able to unify matter and the forces in one rubric of vibrating strings. This interesting idea of extra dimensions comes in, and even that can be leveraged to yield other vibrations that can account for the generation, the family structure of the particles, as Edward is talking about. This thing called string has given insight into black holes, allowed us to understand the entropy of black holes. But, on experimental front, string's not done so well as yet, in terms of uniqueness of a unit. Well, so when you take all that together, David, if you don't mind, how would you assess the state of string theory?
B plus.
B plus. Nice and concise. Edward, however you want to answer that. It doesn't have to be a grade. It can be however you describe it.
Well, I think a letter grade won't do justice to the situation. I think there are a lot of reasons to think that string theory is on the right track. And I think what has been accomplished in theoretical physics in the last 40 years is much more than would have been if we hadn't had the good luck to stumble upon string theory as a way of getting beyond the framework we know. But as for how far we are in the direction of wherever it is we're trying to get, there's no way to know. And as you know, life does not, unfortunately, come with guarantees.
Andy, the last word.
Okay, well, first of all, I want to emphasize that string theory is not what we were doing in 1984.
Right.
String theory has now come to be a word that is used for everybody who is working on anything that is going beyond the standard laws of physics. I myself, trying to push beyond the edge of what we know. I have not, I'm regularly referred to as a string theorist, though I myself have not written a paper. Of my 80 papers in the last 10 years, 2 of them are
string theory proper.
String theory proper.
Yeah.
So it really is everything that we're trying to do. But I think, and almost all of that is inspired by taking lessons from what we have learned from string theory proper. But I myself, and everybody looks at the different axes on which you might evaluate the subject. Everybody should make up their own mind. But I'm giving it an A+. Otherwise, I wouldn't be working on it. and I think I am very excited about what we are going. There has not been a moment since I was a graduate student in which, except for the 1 year I spent on string field theory and the 2 things on higher derivative gravity, let's forget those. But there has barely been a moment when I wasn't involved, when people around me weren't involved in something that seemed like really was pushing forward the edges of knowledge in some important way. And that is more true now than ever, I think.
Thank you.
So I'm giving it A+.
Yep. And I will say that, my most exciting times, David, we never really had an opportunity to work together, but the time I spent at the Institute for Advanced Study, Edward, when we were working on topology change in different ways, most exciting times of my life. And you and I were working on black holes turning into elementary particles and topology change as well, the most exciting thing. So thank you so much for the way that you all have enriched my life. And please join me in thanking all of these gentlemen for this conversation.